All right, we're going to start our new unit today. It's on electromagnetic radiation. What is electromagnetic radiation? In Science 9, you learned a little bit about it in the context of infrared radiation, heat. You learned what the other types of radiation are, okay, infrared, ultraviolet, X-rays, gamma rays, visible light, all of those other types of EMR, the types that we saw when we watched the video just a few minutes ago. What is electromagnetic radiation, though? Probably didn't learn that in Science 9. EMR is energy. It's energy that's transmitted in a wave-like form. It consists of two waves. Electromagnetic radiation consists of two waves, an electric field wave and a magnetic field wave. Now, here's how it works. You've got this particle, this charged particle that's accelerating over here. Not a charged particle that's sitting there, that won't do it. Not a charged particle that's moving at a constant speed, that won't do it either. A charged particle that's accelerating. That generates a changing electric field, and it also generates a changing magnetic field. So an accelerating charged particle produces a varying electric and a varying magnetic field. Okay, that varying electric and magnetic field can look like a sine wave, like this. Right, a sinusoidal wave looks like this. Now, when that charged particle generates the sine wave that is the electric field, it also generates perpendicular to that a sine wave that's a magnetic field. So you get one that's going like this, let's say on the y-axis, and then you get one that's going like this, let's say on the z-axis. Those two waves are going to be perpendicular to each other, and they're going to be in phase with each other. That means that when you have the crest of one, you have the crest of another. This accelerating charged particle, if it's just accelerating for a brief time, then you're not going to get this continuous wave, but rather just a pulse. Just essentially the crest or the trough of an electric field, or the crest of a trough of a magnetic field. It's going to go like this. The electric field wave, the magnetic field wave perpendicular to that and in phase with that. Now, here's the critical nature of this. Here's what Maxwell discovered, or at least Maxwell hypothesized, in terms of the movement and the production of electromagnetic radiation. He suggested that the changing electric field would make a changing magnetic field, and the changing magnetic field would make a changing electric field. So you've got this wave that's the electric field right here on this side of the room. You got this wave that's the magnetic field. This electric field wave ends up producing a magnetic field wave that looks like this. The magnetic field wave that looked like this, that we started with, ends up producing an electric field that looks like this. So the net effect of that, if you take a look at my fingers here, the net effect of that is you end up with an electric field wave like this and a magnetic field wave that's perpendicular to that looks like this. They end up propagating or moving in phase with each other like this. Okay, if you can, this is kind of hard to do. Can you see what I'm doing there? You got one sine wave on the y-axis and another sine wave on the z-axis here, in phase with each other, crest with crest, trough with trough. It all happens initially because that accelerating charged particle generates a changing electric and a changing magnetic field. Then the changing electric generates more magnetic, and the changing magnetic generates more electric. So, ultimately, if that charged particle is only accelerating for a short time, then we get one pulse in one pulse. That generates another pulse and another pulse, like this. The ones that generated the new wave are now gone. So the wave that was there is gone. It's made another wave right here. That in turn makes another wave right here, and then that disappears. That in turn makes another wave over here, and that disappears, and so on. So what you end up getting is a bit of the wave that's moving from where it was produced over there to over there. How do you keep a continuous wave moving? You got to keep accelerating the charged particle. So when this wave and this wave produce this one and this one, you have to have the accelerating charged particle still accelerating to fill in what was just lost, to fill in that part of the wave that just was lost when it produced this part of the wave. Does that make a little bit of sense? All right, let's take a look at this here. Okay, basically, it summarizes what we just said. The next couple pages summarize what we just said. Maxwell knew that a changing magnetic field makes a changing electric field. The changing electric field makes a changing magnetic field. Notice it didn't say a magnetic field produces an electric field and an electric field produces a magnetic field. In order to have this happen, it needs to be a changing electric field in a changing magnetic field, not just a constant one. And in order to get a changing electric and changing magnetic field, you need an accelerating charged particle, not just a charged particle that's at rest, and not just a charged particle that's moving at a constant speed, but rather one that's accelerating. Once it's been made, this all happens so quickly. The electric field generates the magnetic field, and the magnetic field generates the electric field so quickly that this wave travels at an incredible speed, 3 times 10 to the 8 meters per second, which is about 1 billion kilometers per hour. It's about 50, roughly, 50 one-way trips across Canada in 1 second. Again, these electromagnetic waves, these waves of energy that are transmitted in a wave-like form via these changing electric and changing magnetic fields are produced by charged particles, but not just charged particles at rest. Charged particles at rest would generate an electric field, not a magnetic field. Not just charged particles that are moving at a constant speed. They would generate an electric field and a magnetic field, but they would be constant electric and magnetic fields. But rather, they've got to be generated by accelerating charged particles that are speeding up or slowing down. That's the only way you're going to make the changing electric and the changing magnetic field. And that's critical to this whole thing, because if they're not changing, they're not going to produce the next one. The electric field won't make the magnetic field if the electric field's not changing. And the magnetic field won't make the electric field if it's not changing. Let's take a look at the applet that we see up on the screen here now. This shows us the production of this electromagnetic wave. Where the X, Y, and Z axis intersect, that's essentially where the charged particle is accelerating. As that charged particle accelerates, it generates a changing electric field, which is represented by the red here. It also generates a changing magnetic field, which is represented by the blue. Now you can see that that red wave is moving and the blue wave is moving. It's moving not because it's just for no reason traveling from one place to another, but rather the electric field wave that we have right here at the beginning ends up producing the magnetic field over here. And the magnetic field over here ends up producing an electric field down here, which produces a magnetic field over here, and so on and so on and so on. So it ends up moving outwards along the positive x-axis here because one wave produces the next, and the next produces the next. Now this wave is one in which we have what's causing the next part of it, the electric field and the magnetic field that's causing the next part of it being replaced. So it's not disappearing. It's not just a wave pulse traveling along the positive x-axis. It keeps being replaced. That must mean that the charged particle is still accelerating. Maybe it's going back and forth. Maybe it's like AC current in your house that oscillates back and forth. Speeds up, slows down, stops. Speeds up, slows down, stops. Back and forth, back and forth, back and forth is going to constantly produce this changing electric and magnetic field, which is going to replace the electric and magnetic field that disappears when the next part of it's been produced. Question? Where would the particle be at? It would be at the intersection of the X, the Y, and the Z axis. Which one do we have as our electric field? The red one is the electric field. That would mean that it would be oscillating, I believe, along the y-axis. If the charged particle is oscillating along the y-axis, it's going to produce the electric field parallel to that and the magnetic field perpendicular to that. Does that make sense? It's a little bit difficult to see the exact pattern that's produced here, the sinusoidal nature of it, because it's not just a charged particle that's traveling at a constant speed. Then the electric field would be circular. The magnetic field would be circular, and the electric field would be constant. But since it's oscillating back and forth, that's what's causing the change here. It's just difficult to see, to do that analysis and everything like that. Now, electromagnetic radiation, EMR we'll call it for short, electromagnetic radiation or EMR exhibits certain properties of waves, but it also exhibits certain properties of particles. We'll talk about those particle properties a little bit more as the unit goes on. For now, we're going to make the assumption that EMR is a wave. We're going to make that assumption because of 4 properties that have been observed that are in electromagnetic radiation that are wave properties. Look, if this is a wave property and it's observed with EMR, then EMR must be a wave. Okay, the first one that we see there, or the last one that's written down here actually, but the first one that I want to look at is refraction. Refraction is the bending of a wave. When a wave goes from one medium to another, when one material to another, it's going to change speed. As a result of that speed changing, it's going to change direction. That directional change is refraction. Now, waves do that. EMR also does that. So that tells us, at least it supports the wave nature of EMR, the notion that these EMR, whatever they are, waves, whatever they are, bend when they go into a new medium. They change direction when they go into a new medium. You guys have all seen this before, right? Here's a pool of water or a glass of water, and here's a pencil or a stick going into that water. It looks like it's bent. At the boundary between the water and the air causes it to look like it's bent. It's not really bent. But because of light bending, the light that's reflecting off of the pencil underneath the water bending when it reaches the boundary, it looks like it's bent. Okay, refraction is the bending of light. Since EMR undergoes refraction, it supports the wave nature of it. What's diffraction? You learned about that in Physics 20 as well. Diffraction isn't the bending of a wave, rather, diffraction is the spreading out of a wave. So my wave is represented by the green line here. There's a boundary there, there's a barrier there, so most of the wave is going to reflect when it hits that barrier, but there's a little bit that hits the opening in the middle there, and when it does that, that part of it's going to go right through. But it doesn't go straight through and go like this. It goes straight through and then spreads out when it gets to the other side. That's called diffraction. The spreading out of a wave is called diffraction. It happens in waves, but it also happens in electromagnetic radiation. So again, more evidence to support the wave nature of EMR, the fact that it undergoes diffraction. Interference you learned about in Physics 20. Interference happens when 2 waves come together. You get a crest of a wave and a crest of a wave. They hit each other, they make a bigger crest. It's constructive interference. When a crest meets a trough, it makes destructive interference. I know in my class we did the demonstration with a slinky, and I'm sure in Mr. Kader's class you did as well, where you sent one wave pulse down, another wave pulse down, both on the same side. It makes a bigger wave, bigger crest, constructive interference. That's a property of waves. But EMR undergoes interference as well, constructive and destructive interference. That supports the notion that electromagnetic radiation is a wave. Okay? It supports the wave nature of electromagnetic radiation. So all 3 of these properties of waves happen with EMR, suggesting that EMR is a wave. Now, polarization is the only one really that we didn't talk about in Physics 20. Polarization is like a filtering of a wave. Let's draw a picture of a piece of plywood here. You got a piece of plywood with a slit or an opening cut in that plywood. Now, if you take, say, a skipping rope and you flick the skipping rope like this vertically, then you're going to make a vertical wave. But if you flick it horizontal, you're going to make a horizontal wave. If you flick it diagonally, you're going to make a diagonal wave. Let's say you've got 100 skipping ropes and you're flicking them in random directions. So they end up with some of the waves vertically like this, some of the waves horizontally like this, some of them like this, some of them like this, and so on. If I put each one of those skipping ropes through this hole, through this opening in the plywood, there's only one type of the wave that's going to make it through. That's the skipping rope that I'm flicking vertically, this one right here. This one's not going to make it through. This one's not going to make it through. This one's not going to make it through. We'd say those waves have been polarized vertically. Only the vertical waves will make it through. The horizontal, the diagonal waves won't make it through. It's been polarized vertically. Does that make sense? I'm going to do a little demonstration for you here right now with some polarizing filters with light. These are not very good polarizing filters, but they'll do the job here. Literally, if I can keep them together, that's the That's the biggest challenge here, because they like to fall apart on us. Most of them we've got taped together with Scotch tape here now, so it shouldn't be an issue for us. I'm going to put one of these polarizing filters in front of the projector light here. What you're going to see is most of the light, most of the wave is filtered out. So you're going to see only one component of the wave that goes through. I'm not suggesting that it's only going to be the electric or the magnetic field. It's going to be both of them. But it's going to be both of them corresponding to a certain component of one of them. So let's say, look at my arms here. I've got one arm representing electric, one arm representing magnetic. Some of the waves are going like this, some are going like this, some are going like this. Okay? Either this will go through, or this will go through, or this will go through, but not all of them. So the electric field wave that corresponds to the way this filter is polarized, and its corresponding magnetic field wave will make it through. So what you should see here on the screen is a dimmer light, because you're not allowing all the light to go through. Try to do this so that my fingers aren't getting in the way here either. Yeah, you also see it, depends on which way I have it oriented, it can change colors as well. It was purple, it was green. I'm going to turn this ideally so we get gray here. Yeah, it's purplish gray. Okay, good enough. You can see that the light on the screen isn't nearly as bright as it was now, or as it was before, because again, a lot of that light has been filtered out. It's been polarized. When I take the other filter, I can do exactly the same thing. And again, I've polarized it vertically, let's say, so that it filters out all but the vertical component of the electric field and its corresponding magnetic field wave. Watch what happens when I put them both together. Basically the same thing, right? It's a little bit darker now because I've got two filters in front, but it's basically the same thing. Watch what happens when I take them both, put them there, but I turn one of them. That's all I'm doing. I'm not putting a hand in front. I'm just turning one. It goes black. It's like the projector's turned off. Keep turning it. What happens? As I keep turning it, it reappears. Turn it again. Goes black. Turn it again. Reappears, and so on. Why is it doing that? What's happening there? Yeah. You're blocking every wavelength of light. That's right. You've got this piece of plywood right here that's allowing only the vertical to go through. What we really should say is it allows nothing but the vertical to go through. It filters out everything except the vertical. Let's look at this one that filters out everything but the horizontal. If we put them both together now, the blue filters out everything but the horizontal. The black filters out everything but the vertical. What makes it through? Nothing makes it through. We just observed polarization of light. Polarization is a property of waves. If light or if EMR undergoes polarization, then it must be a wave. So we've learned four things today to suggest that light, or EMR in general, is a wave. Refraction, the bending of light. Diffraction, the spreading out. Interference, when they come together. And finally, polarization, the filtering of EMR. Does that make sense? Got a couple multiple choice questions to work on here right now. The first one shouldn't take us any more than about 30 seconds. You take a read here, see what you can do, commit to an answer, and then we'll take a look at it in class here. All right, let's take a look at this one. It says EMR is produced by the charged particles that are moving what? A at the speed of light, B with zero acceleration, C with a changing velocity, D parallel to a fixed magnetic field. How many people said A for this one? B, C, and D. Good. C is the correct answer. What I was worried about when you were doing this question is that you'd get caught up with this word. You'd say, oh, I remember something about accelerating charged particles. I see the word acceleration. That must be the answer. Okay. What does acceleration mean? It means a changing velocity. So C is clearly the answer. Okay. Charged particles that are accelerating generate EMR, not ones that have a zero acceleration. All right, next one. 105, Maxwell's work contained the new idea that, take a look at these four options and see if you can come up with an answer for that one. How many people said A, an electric current in a wire produces a magnetic field that circles the wire? B, C, D. Okay, the answer is C. Maxwell's work contained the new idea that an electric field that changes with time generates a magnetic field. Now, it also contained the idea that a changing magnetic field generates a changing electric field, and that it moves perpendicular to both of those waves. Okay? But that's at least part of what he said. How could we change this question? How could we make this question correct for A? Okay, what could we change in the stem of the question to make A the correct answer? Yep. No. Yeah, let's change it from Maxwell to another guy. What guy suggested that an electric current produces a magnetic field that circles the wire? That Ørsted, yeah, good. That guy. As Nick said, it's Ørsted. How could we change it to make B the correct answer? A current is induced in a conductor that moves across a magnetic field. It wouldn't be Maxwell, it wouldn't be Ørsted, rather it would be this guy or this guy. Two guys suggested that if you move a conductor across a magnetic field, then you're going to generate a current. It was Faraday and, no. Faraday and Henry, right? Joseph Henry and Michael Faraday. Good. All right. How is Maxwell's theory of electromagnetic radiation supported by experiment? We zoom forward a little bit to a guy named Heinrich Hertz. That name should seem familiar to you. When you talked about frequency of an object moving in a circle in the circular motion unit of physics 20, you talked about Hertz. When you talked about the frequency of simple harmonic motion, you talked about Hertz. The frequency of a wave, you talked about Hertz. And that was named after Heinrich Hertz because he did a lot of work with EM radiation, which has a frequency associated with it. So they named the unit for frequency after him. Just drop your pens for a second and just watch what I do, and then you can copy it out, okay? The apparatus that he used is called a spark gap apparatus. It consists of a step-up transformer. A step-up transformer, you don't really need to know how it works, but in essence, it produces either a smaller voltage than you started with, that would be a step-down transformer, or a bigger voltage, a bigger potential difference that you started with. That's a step-up transformer. Here, we're going from 3 loops of wire to more loops of wire, so we're going to produce a bigger voltage. We're increasing the potential difference to a bigger value. The reason we want to increase the potential difference to a bigger value is so that we've got a chance at causing electrons to jump across that little gap. There's a gap in the wire. If we have 1.5 volt battery, we're not going to cause electrons to jump across that gap. But if we have 50 volts or 100 volts or whatever, then we got a chance at causing electrons to jump across that gap. Hertz reasoned that as these electrons jump across the gap, they're going to have to accelerate. So if we detect electromagnetic radiation, then it must be that the accelerating charged particles generated it, and therefore Maxwell's theory must be correct. Now, how are we going to detect it? We put an antenna there. How does an antenna detect EMR? Well, if EMR truly consists of a changing electric and changing magnetic field, as Maxwell suggested that it did, then an antenna, a conductor, should have an electric current induced in it when exposed to that changing electric and magnetic field. So the idea here is this. If we can detect a current in this antenna, then there must have been a changing electric and changing magnetic field present. That changing electric and changing magnetic field is Maxwell's electromagnetic radiation. What was it caused by? Well, it must have been caused by the accelerating charged particle, which is even more evidence to support Maxwell's theory. Accelerating charged particles cause EMR, and EMR consists of electric and magnetic fields that are both changing. We fire this thing up, lo and behold, we detect an electric current in the antenna. Hertz reasons that that means that Maxwell's theory that it consists of an electric and magnetic field that are changing and produced by an accelerating charged particle must be correct. The type of EMR that he detected first, he named radio waves. Radio waves, as you know from the video that we saw yesterday and today, are the smallest frequency EMR. The reason that he detected those before he detected anything else is because they're the easiest to make. He wasn't intentionally making radio waves. He made the easiest kind of EMR that he could. They just happened to be these low-frequency EMR waves, and he named them radio waves. Okay, now you can write this down. All right. The last slide that we have up for the day gives us the entire spectrum that we saw in the video that we showed you yesterday and today. Start off with the radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. There's another way to remember the order of this as well, though. Let's start off with visible light. Visible light consists of 7 colors: Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. What's going to be below red? Infrared. Infra means below. So infrared means below red. What's going to be above violet? Well, ultra means above. So ultraviolet is going to be above violet. That tells us right away the 3 middle types of EMR: infrared, visible light, ultraviolet. We'll look at the other kinds: X-rays, gamma rays, microwaves, radio waves. X-rays and gamma rays sound a lot more dangerous than microwaves and radio waves do, so let's put them up on the far side of it, the right-hand side. Radio waves and microwaves sound a lot less serious than gamma rays and X-rays, so let's put them on the left-hand side, down on the infrared side. Notice that we've got these ranked, or we've got these classified in 3 different ways in terms of frequency, energy, and wavelength. Radio waves have the lowest frequency. Gamma rays have the highest frequency. Similarly, radio waves have the lowest energy. Gamma rays have the highest energy. Wavelength works exactly the opposite. Wavelength, when we have a high wavelength, it means we have a low frequency. So we're going to say that radio waves have low frequency, low energy, and high wavelength. And gamma rays have a high frequency, high energy, and a low wavelength. In other words, the frequency increases as we go from left to right, the energy increases as we go from left to right, and the wavelength decreases as we go from left to right. There's a very good chance on your next unit test you will have to rank, not all of these, but some of these in terms of increasing wavelength or increasing frequency, whatever. Think of the song. Okay, remember it in terms of frequency, and then answer the question that you need to answer based on that. What are radio waves exactly? Where do you see radio waves? Okay, you listen to the radio, you watch TV. Okay, literally, radio, TV, radar, okay, uses radio waves. Where are microwaves used? Well, there's an obvious one for this one. Microwaves are used in microwave ovens. They cook food. The resonant frequency of water corresponds to the frequency of microwaves, which means that when these microwaves strike the water, they cause the water to vibrate. That produces heat. That heat transfers to the inner part of the food by conduction. It cooks food by resonance. It cooks food by causing the water molecules in that food to vibrate. But microwaves are also used, besides microwave ovens, in cell phones. Much less power. You know, a microwave oven uses 1,100 watts of power. If you try putting 1,100 watts of power on the side of your head, you're going to start boiling the water that's in your head. That's not good. Eventually, your head would probably explode, yes. But we're not using anywhere close to that kind of power, right? Infrared. What's infrared? Well, infrared is heat. It's thermal energy. It's heat. It's used in all kinds of places, including obvious places like cooking. Infrared is also used in night vision. Some types of night vision goggles use infrared. Okay, some don't. Some just pick up ambient visible light, but some use infrared. It's also used, you saw in the video, it's also used in remote controls. Visible light, of course, that's obvious, right? The different types of visible light, where they're used, that's the kind we see all the time. Ultraviolet. Ultraviolet produces sunburns, black light, yes. Ultraviolet produces sunburns, black light. Kills germs like bacteria, viruses. We can sterilize things with ultraviolet light as well. Sorry? Bees? What about bees? Oh, is that right? Okay, I didn't know that actually. Patrick says that bees only see ultraviolet. So apparently I didn't know that, but apparently bees only see ultraviolet. So, okay. So X-rays are obviously used for imaging. Sometimes it's medical imaging, but sometimes it's also other imaging. We saw in the video detecting bombs in ladies' purses at airports or whatever. X-rays are used in all kinds of imaging when you want to see through something. The idea is that X-rays have a high penetrating power because of their energy. It's like you take visible light photography, right? Photography with a normal camera. The visible light reflects off of something, gets detected by the CCD at the back of your camera, and allows you to see an image. Well, X-rays penetrate more. So if you have X-rays shining on, let's say, a person, it's not going to reflect off of their skin, it's going to reflect off of their bones. So when it gets detected by that CCD detector in the back of your camera, for lack of a better term, you don't see the person's skin, you see the person's bones. You see inside things because of the high penetrating power of X-rays. So we'll say it's used in imaging, but it doesn't necessarily have to be medical imaging, as it often is. It can be any kind of imaging, right? Gamma rays. Gamma rays are often used in cancer treatment. Disinfecting things, gamma rays can be used for. Yep.
So the only reason that microwave water is the same.
Yeah. No, the microwaves, I mean, why you look at this in terms of frequency and in terms of energy. Microwaves have lower frequency and lower energy than visible light do. Visible light doesn't cook food, but microwaves do. So there's got to be something special about it. Not, okay, it's really high up on the spectrum, it's got a lot of energy, whatever. There's got to be something special about the microwaves that cause the food to cook. The thing that's special about it is the frequency of it. The frequency is in the range of that resonant frequency of water, so it causes water molecules to vibrate. We talked about this in Physics 20. When you jump on the bridge at just the right frequency, what happens to the bridge? It starts vibrating more and more and more, right? Okay. When the wind was blowing on the Tacoma Narrows Bridge. You guys saw the video in my class. I think you probably saw it in Mr. Creder's class as well. The wind's blowing, the wind's gusting at that right rate. It causes the bridge to start vibrating more and more and more, and eventually to fall down, right? When you match a resonant frequency, you cause vibration. So when you match the resonant frequency of water, you cause vibration in the water. The resonant frequency of the water corresponds to microwaves, so we match it by applying microwaves to it. Water vibrates. That produces heat. As you produce heat, that heat conducts to the inside of whatever it is that you're trying to cook and cooks the food. So the only way it works, the only reason it works, yeah, your question, back to your original question, the only reason it works is because of the resonant frequency of water.
So something water at the frequency.
Well, if you had, yeah, yes, if some, theoretically, I suppose, yes. But remember that we're going to see in just a few minutes the frequency range here. The amount of times per second that thing would have to vibrate would be astronomical. So physically, you're not going to be able to do that. Okay? Theoretically, you could, but physically, you couldn't. Yep. I don't know exactly, to be honest, how an MRI works. I'm not sure what range it would be in because I'm not sure the technology exactly that it uses. I've had one once before, but again, I wouldn't want to say where it's under because I don't know exactly what the technology is that makes it work. I'm sure we could look that up pretty easily, but I just haven't. Look it up and let me know, okay? Good question. Let's take a look at the causes of each of these types. So this is some of the things where they're used or some of the places we see them. Let's take a look at the causes. We're going to group these together, some of them together at least. Radio waves and microwaves are both produced in the same basic way. They're produced by oscillating electric charge. What does oscillating mean? Back and forth, back and forth, back and forth. The electric charge that's going back and forth. Okay, that could be something as simple as an AC current. The power that we use in our houses is AC current. It's electrons going back and forth, right, Rob? Back and forth. As they do that, they've got to speed up, then slow down, then change direction, speed up, slow down, change direction, and so on and so on. That generates low frequency radio waves, and if we tweak it a little bit, it can generate microwaves, higher frequency. Infrared, visible light, and ultraviolet are all produced in the same basic way. They're all produced by transitions of electrons. In atoms. Now, to get different types of EMR, or infrared, visible light, ultraviolet, different frequencies, we use different transitions. And we also use different atoms. So, in a transition from the third level to the first level in hydrogen may produce one type of EMR, and the transition from the sixth level to the fourth level in lithium may produce a different frequency of EMR. But in general, these three types are all produced by electrons making transitions from higher levels to lower levels in the atom. X-rays are produced by rapidly decelerating electrons. Electrons, we accelerate them to a really, really high rate of speed. An incredible speed, like 10 to the 5, 10 to the 6, 10 to the 7 meters per second. And then we smash them into a target. We hit something with them. Those electrons have got to stop really, really quickly. And they had a lot of kinetic energy. That kinetic energy has got to go somewhere. It goes off in the form of an X-ray photon. So X-rays are produced by rapid deceleration of electrons. An X-ray tube accelerates them to that high speed, and then we smash them into this target. That causes them to slow down and stop really quickly, which produces the X-ray. And finally, our gamma rays here, our last type of EMR, are produced by nuclear decay. And what I mean by nuclear decay essentially is matter, or mass, converted to energy. We'll talk more about that later on in this unit, how matter can be converted to energy. But in essence, anytime you have a nuclear reaction, including a fission reaction, a fusion reaction, radioactivity, you get gamma rays produced where matter, mass, disappears. And it's changed into energy. That energy is in the form of a gamma ray. How do they use gamma rays for treatment at a hospital? Where do they get them from? Well, you don't just order gamma rays from your supplier. What you order from your supplier is radioactive material. The radioactive material sits at the hospital in the machine. It decays, and as it decays, it produces gamma rays. As matter is converted to energy from this radioactive material, it generates these gamma rays, which are used to obliterate cancer cells and for a number of other purposes as well, diagnoses, etc. Finally, the last thing that I want to do with you today, same slide, good news and bad news. What do you want first, the good news first or the bad news first? Bad news? Okay. Here's the bad news. Each one of these types of EMR, all 7 of them, have a specific frequency range associated with them. They also each have a specific wavelength range associated with them and a specific energy range associated with them. That's 21 different ranges of numbers that we have to know for our test. That's the bad news. Now, do you want the good news? The good news is you have me as a teacher. Oh, no, it gets, wait a second. It's not just that. That's good news in itself, but it gets better. The good news is you only really have to remember 3 of them, 3 of the 21. I used to teach, all the different frequency ranges, all the different wavelength ranges, and then it occurred to me there's no reason why we have to memorize all of those. We only need to memorize 3 of them. Here's why. Microwaves, which have a frequency range of about 10 to the 9 to 10 to the 12 hertz, are above radio waves and below infrared. Visible light, which have a frequency range of about 4 times 10 to the 14 to 7.5 times 10 to the 14 hertz, are above infrared and below ultraviolet. X-rays, which have a frequency of about 10 to the 17 to 10 to the 20 hertz, are above ultraviolet and below gamma rays. If we get a frequency given to us, a type of EMR given to us, and we're asked to identify what it is a frequency of 10 to the 10, well, we know it's going to be microwaves. If it's 10 to the 14, 6.5 times 10 to the 14, we know it's visible light. If it's 10 to the 18, we know that it's X-rays. What if it's 10 to the 22? We don't have to memorize that 10 to the 22 is gamma rays. If we have memorized that X-rays go up to 10 to the 20, and we get 10 to the 22, we know it's gamma rays. If we get 10 to the 13, what is it? It's got to be infrared. We don't have to have that memorized. 10 to the 4, what is that going to be? Radio waves. Again, we don't have to memorize all 7 of them. If we memorize and memorize well these 3, then if something falls in between or on the other side of microwaves or X-rays, then it's got to be one of the ones that falls, one of the ones on the spectrum that we haven't memorized. In other words, we've got to be able to tell what it is based on its position. That tells us all the frequencies. So we've got all the frequencies taken care of by memorizing 3 ranges. What about the wavelengths? Well, the good news is we don't have to memorize any of the wavelengths. In Physics 20, you guys learned about an equation, V is equal to F times lambda. Remember that one? It's the wave equation. Let's rearrange it. F is equal to V over lambda. The speed of EMR is 3.00 times 10 to the 8 meters per second. If you're given a wavelength and you're asked to identify what type of EMR it is, then figure out what the frequency is. Say 3 times 10 to the 8 divided by the wavelength. That gives you a frequency, and then do what we just did. Compare it to the 3 frequencies that we've memorized. If it's not one of those 3, then it's got to be something that falls in between. Finally, for energy, there's an equation that's similar to V is equal to F times lambda for energy as well. I'm not going to tell you what it is right now. We'll talk about that later on in the unit. For now, just trust me that we can find the frequency from the energy if we need to. So you're given a particular frequency, you're given a particular wavelength, you're given a particular energy. You can identify what type of EMR it is by converting it to frequency and then comparing it against the 3 frequencies that we've got memorized. We got that? So it sounded really bad when I told you had to know 21 different things. You do have to know 21 different things. But the good news is that 18 of them you can figure out on the fly. You only have to memorize 3 of them. All right, your homework for today, for tomorrow I should say, is some check and reflect questions. Check and reflect 13.1. I don't have the page number written down there. I'm sorry, I forgot to do that. The questions that I want you to work on, please, for homework for tomorrow are questions 1 to 2. I want you to work on number 5. I want you to do number 7 and 8. And 10 to 14. You have about 9 minutes left in class. Get a good start on those now. Ask me some questions. And then we'll check them over tomorrow.